maintenant vous disposerez du temps nécessaire pour nous exposer l'essentiel de votre travail.
Merci. In the name of Allah, the most gracious, the most merciful, prayer and peace upon the messenger of Allah, peace be upon him. Thank you, Professor Rashid, for accepting to be the president of my PhD defense. Great thanks to Professors Bali, Zinati, and Shade for all their comments and valuable remarks. Today, I wanted to thank my supervisor and co-supervisor for all their supports, advice, and attitude with me during my PhD trial. To all our entities, welcome to my PhD defense. The title of my PhD thesis is Correlation between Permeability and Carbonation. It's its influence on the service life of the reinforced concrete structure. I want to start my presentation with this house. This house is considered as a historical building by the French government. Well, why? What this house means for civil engineering. This means a lot because this is the first reinforced concrete structure built in the world in the 1853. When I saw it the first time during my research, I told myself, what are the questions that the engineer asked during building this house? Maybe how long it will stay in service, or which requirement should we follow, or how long is the service life of this material. We know that everything in our world belongs to service life, and it is important to know its definition. The service life of the reinforced concrete structure is the time for which the structure performs with an acceptable level without requiring unforeseen high cost for maintenance and repair. And this is what we call it durability. Before to enter to details, I want to give you some background about this material that still, since its invention, the first used in the field of construction. Concrete is functional, efficient, and universally available, can be used in high and low technology. And also, concrete is a developmental material par excellence. And some applications, and the one that I love it so much, it is in our university, which is our auditorium. However, and unfortunately, this material suffered from premature deterioration that threaten the human being's safety and limit the economic growth of the country. And the view of the collapsed Morandi Highway Bridge in Genoa, Italy, collapsed in 2018, which is not far from now. Not due to earthquake or other accidental action, but due to reinforcement corrosion. In this case, we ask this, and it causes more than 43 deaths. In this case, we ask these questions. What are the aggressive agents leading to reinforced concrete structural deterioration? How to prevent premature deterioration? And how to ensure the durability of the reinforced concrete structure? I want to try to answer to all these questions, but please allow me to continue my presentation. Reinforced concrete structure are composed principally of two materials, concrete and reinforcement. We have actions that causes the deterioration of the concrete, and we have actions that causes the most common and dangerous deterioration mechanism, which is the reinforcement corrosion. That can be due to the chloride penetration or to the carbonation penetration. In our presentation, I will focus on the corrosion owing to carbonation. You told me why? Because the amount of the CO2 increases because to the global warming effect, and also to the fact that 2 over 3 of all reinforced concrete structure are implanted in environment that favor the reinforcement corrosion due to carbonation. And the standards, in order to ensure the durability, they classified the environment into exposure classes. And for the case of carbonation, we have 4 exposure classes: XC1, XC2, XC3, and XC4. It means if my structure is implanted in XC4, it will suffer from carbonation more than the remaining exposure classes. And the dangerous exposure classes are XC3 and XC4. Why these exposure classes? In order that the standard will give us specification according to these exposure classes. When we go to the practice, we find that we have 2 methods in order to ensure the durability. We have the perspective one and we have the performance one. The perspective one, it is some rules that we should to respect. If we respect these rules, for example, this maximum WC ratio, this minimum compressive strength, this minimum cover depth, my structure will be deemed to satisfy the durability provision. And these rules derive from the deemed to satisfy approach. However, this method faces several disadvantages as being predefined for only low service life. If I need higher service life, I can't use it. And also, in this method, I can't predict anything because I don't have any model. And if the requirements are not met, for example, compressive strength or cover depth are not met, I can't predict the loss of service life and other disadvantages. In this case, the concrete community put much effort in order to develop another method which called the performance-based approach. Besides this method, what does it mean, performance-based approach? It means that the durability should to be based on an indicator of durability related to the transport mechanism of a deterioration process. This method needs robust, industry accepted test method in order to judge acceptable performance. And the main advantages lie in integrated performance approach. In this slide, I will give you the international effort in developing performance-based specification in service life mode. The country that is very advanced in developing this specification is the Switzerland. The Switzerland, they work with durability indicator, and they prescribe value limitations in both case, chloride and carbonation-induced corrosion. And they link, we have the chloride, and we have the accelerated carbonation depth. And they link the DI are prescribed for conformity control, and they link it to the air permeability, which call it Torrent test method. If we go to another country, we find that South Africa are very advanced in developing service performance-based specification, but they work with indexes, non-durability indicator, and they develop 3 durability indexes: the oxygen permeability index, the water sorptivity index, and the chloride conductivity index, as you see here. And the important things in South Africa, they developed 2 service life models. In the case of the carbonation and in the case of the chloride. And the important things, they link the carbonation to the OPE index and the chloride to the chloride conductivity index. And we have another examples in other countries like Canada and Netherlands. After that, I will give you here in this table the summary of all the international efforts. When we focus on this table, we find that permeability has been used by several researchers in order to develop performance-based specification. And when we went deeper, we found that gas permeability has been used in order to predict the carbonation by several countries. And they proposed a model to predict the carbonation relying on the permeability. In this case, we divide our research to 2 parts. The first part, in order to study the effect of carbonation reaction on the oxygen permeability of concrete. The second part, which is to predict the service life at the design stage, but working with in the case of carbonation, but with permeability required, following a probabilistic approach. For the first part, this is our publication in Periodica Polytechnica Civil Engineering, and the outline of this part is as follows. As a background, I didn't write here anything because we didn't find that we have one conclusion. We find that we have many trends. Some researchers find that we have an increase, others find a decrease, and it means that we didn't get that we have clear conclusions concerning the effect of carbonation on the permeability. In this case, we told ourselves we should to enhance this discrepancy by an experimental contribution. In this case, we use this material to achieve the objective. After that, we characterize these materials. Why we characterize these materials? In order to gather all the data necessary to design the concrete, and also to see if our materials are acceptable to manufacture hydraulic concrete. And it was the case of the study. All our materials are acceptable to manufacture our concrete. After that, we went to design our concrete. We followed the Georgoris method. We refer to these two books. And after, in this table, we get the concrete mixtures. You see that we worked with 6 concrete mixtures in order to gather a good range of WC ratio. After that, we should to practice them in order to ensure they give us the targeted service life, the targeted compressive strength or not. We start with mixing. After that, preparation of the standard specimens. After that, conservation and preparation for compressive strength. After that, we have the result. You see that we have low compressive strength until, if we can say, high performance compressive strength. After that, here, we should to mention, we will enter to details for our experimental program. Our experimental program is divided into stages. The first stage is to assess some characteristic, the oxygen permeability, the compressive strength on non-carbonated specimens. After that, all the specimens will be subjected to accelerated carbonation test. We will assess another oxygen permeability, compressive strength, wet variation, besides the carbonation depth measurements. Now into details. For the oxygen permeability test measurements, we follow the modified test procedure developed by Isa Taleh and Fatom Kharshi. This method has been used by several researchers and show efficiency. This is the method, and this method allows us to calculate the apparent permeability following this formula. This is the device, and the main element is the cell, with eliminating the confining pressure and the air cylinder. And also we have another devices as the regulator of the pressure and other devices as the flow meter, the elastic ball, and the gas supply. This method needs specific specimens with holes, as you see here. The casted specimens is given here, and after 24 hours, we demold them, we conserve them, and we sound them in order to get the required thickness, which is 10 centimeters. Besides these specimens, we prepared cubic specimens in order to assess before and after carbonation, the weight variation and the compressive strength. Now, arriving to the first challenge that we face in our experimental program, which is the accelerated carbonation test. We didn't have the accelerated carbonation, and we were obliged to manufacture our own. And in order to manufacture our experimental device, we spent 2 years in order to know all the conditions and in order to see all the requirements following the standard, which we follow the French standard. After spending 2 years, and in order to have a big volume, in order to put as much as we can specimens, we built it with a big volume. And this is make our work, the difficulty our work multiply the difficulty of our work in twice. After 2 years, we manufactured our experimental chamber. The devices that are important is the regulator of the pressure of the gas, is the carbon gas detector. We use this gas detector, and for the humidity and temperature detector, we use this device. Why? Because we should to ensure the required humidity and temperature following the standard. After that, all the specimens will be preconditioned and prepared with double layer adhesive aluminum to allow any directional carbonation penetration, as you see here. After that, all the specimens will be subjected to accelerated condition. But here I should to mention that we should to ensure the humidity. We use the saturated saline solutions, and we work with the nitrate of magnesium that generate 55% of humidity, as you see here. After that, we will assess again all the characteristics, the oxygen permeability, the compressive strength, the weight variation, besides the carbonation depth. This is an example. This is a carbonated zone, and this is the non-carbonated zone. After that, we did microscopic tests, some images in order to characterize the carbonated zone and the non-carbonated zone. This is the overall, this is the summary of the experimental program. Now arriving to the results and discussion. Before plotting any figures and analyzing any results, we prefer to work with the intrinsic permeability rather than the apparent permeability. And in order to obtain one value, we should to plot here 3 values of Ka. And for the non-carbonated concrete, for the carbonated concrete, we can spend a day in order to have just one value of Ka. And imagine how much the effort that in order to have just one value of KENT, which is the intrinsic permeability. So what we will see, all as function of the intrinsic permeability. First, and this is an example how to obtain it. With the linear regression and the intersection with the y-axis is the intrinsic permeability. After that, we started our analysis with developing some of the oxygen permeability correlations with the compressive strength and with the WC ratio. And we find that we have power correlations and good indications we obtained with these indications. After that, we studied the effect of carbonation on the concrete compressive strength. This is the results, and the analysis of these results show that carbonation reaction considerably affects the concrete compressive strength. As the carbonation depth increases, the concrete compressive strength increases. F3 has reached 88% increase of its compressive strength, which corresponds to the highest carbonation depth. We try to justify these results with the weight variation, and we find that we can rely on the weight variation in order to have an approximate indication concerning the carbonation progression. After that, arriving to the main effect, which is the effect of carbonation on the oxygen permeability. We prefer, this is the results. This is the results. We prefer to work with the relative intrinsic permeability. And what we found that we have 2 different relationships. One for the high performance concrete and the other for the ordinary concrete. And this is the formula of the correlations with the indications. What we found, as not expected, carbonation reaction considerably affect the concrete permeability. As the carbonation increases, the permeability of concrete increases. And also we find that we have good correlations for both relationships. In order to justify these results, which is the increase of the permeability, we worked with the same images of the carbonated zone and the non-carbonated zone. And we found that with the image, we can generate a binary images in order to calculate the porosity. And you see here that the carbonated zone, the black points are the porosity, are much higher in the non-carbonated zone. Arriving to the conclusions of the part 1, we found that for the non-carbonated concrete, the assessment of the oxygen permeability through the WC ratio and compressive strength shows the existence of good relations. Also, the carbonation reaction has a positive effect on the concrete compressive strength. Furthermore, it was observed that high-performance concrete is more influenced by carbonation in comparison with ordinary concrete. The concrete carbonation reaction led to the formation of a new element that induced the compressive strength and the concrete weight to increase. These results are observed for all concrete or concrete mixtures. The results obtained show that permeability increases as carbonation progresses. Furthermore, this increase depends on the compressive strength of concrete and the effect of carbonation reaction on the oxygen permeability is more significant in high performance country rather in ordinary country. Some images justify the increase of the oxygen permeability via the observation of the creation of larger pores that influences the interconnectivity of the pore system. Now arriving to the conclusions of part 1, now we can enter to the second part with confidence. We ensure that we can rely on permeability in order to predict the carbonation. For the part 2, this is the outline. As a background, let us remember what we have seen at the beginning. At the beginning, we've seen what does it mean service life. After that, we've seen how to ensure the durability. After that, the international effort in developing service life model and performance-based specification. And after that, the summary. From here, I will continue my presentation. Here you see that the durability or the service life model, in the case, they are based on an indicator of durability that can't be assessed on real creep. What does it mean? I shoot 2 drill cores and to test them at the laboratory. And in the case of carbonation, I shoot 2 drill cores and to do the test as Sombero test or the OPE test. And in order to develop our approach, we told ourselves that we should to develop our approach relying on a test method that we can apply it on site. In this case, we told ourselves that we should to gather all the tests that exist in the world. And after that, we will select the most appropriate. We gathered all the tests. We find that we have, in order to calculate gas permeability, we find that we have fixed test. After that, we have Hilshoff and Schoening test method. We have the exponent test method. We have the autoclamp test method. Here it is applied in nuclear power station. So we can rely on this test method. After that, the Torrent test method. And after that, the Taleh and Kharshi test method. And after that, the Sombero test method. In order to make our selection, we compared all these tests. And when we compare these tests, we find that Torrent test method gather the highest points. And in order to select which test we will select, the criterion that is important if the tests are standardized or not. And we find that we have 3 tests that are standardized. The Torrent test, the Sombero method, and the oxygen permeability. Another criteria in order to select our test, if the tests are applicable on site or not, and if it is destructive or not. And this is only available for Torrent test method, and not available for Sombero or the South Africa test method. Besides, the Torrent test method allows correction for the moisture, and this is important. In this case, we select to work with the Torrent test method. So we will search of the data with this method, and what we found something interesting. We found that we have already relationship with permeability of Torrent and accelerated carbonation. And the story of our research started in 2009 by the original work of Teruzzi. After that, this work, the same approach, has been used by Neves in order to predict the residual service life. After that, the same approach, we used it in our research in order to predict the service life at the design stage. Now, before to enter to details, I show you here the criteria that we can use in order to get durability-based design. We have the deemed to satisfy approach, we have the avoidance of deterioration, we have the semi-probabilistic, and we have the full probabilistic. In our development, we will follow the full probabilistic because it is the most sophisticated, accurate method to assess the durability of the reinforced concrete structure, but requires much knowledge of statistical tools. Now, in order to develop our lifetime function, we start with the first law of Fick. This is of natural conditions of carbonation. And in order, I told you that we get already relationship between permeability and accelerated completion. And in order to use this method, we need to make the conversion from accelerated to natural. In this case, we use the relationship that we find that developed in Nevesh in 2013. This is the formula in order to make the conversion from accelerated to natural. And for the relationship between accelerated carbonation and permeability, we use the relationship developed also by Nevesh in 2015. This is the relationship. Here you see KCA equal A KT. This KT is the air permeability coefficient of Torrent, and the A is the parameter related to the type of the cement. Now, introducing equation 3 and equation 2 in this equation, first law of Fick. And considering here something important, that the end of service life of my structure is the reinforcement depacifications. I will not consider the propagation period, just here, the reinforcement corrosion, the initiation period. If we consider this, our lifetime function, which is formula 1, will become this. And this is our basic formula here. In order now to solve this formula, we will should to know the parameter. We have here the cover depth, the KE, and we have here the relationship. These parameters are not deterministic. They have uncertainty, and we consider them as a random variable. And so the solution of this formula is a random variable as well, as you see here. In this case, we should to base our work on a probabilistic work. This is the probability of failure event. This is the design working life and the probability density function. In order to solve this integral, it is necessary to know the distribution of the random variable in equation 4. This is the lifetime function, and for the cover depth, it follows a normal distribution. For the KE, it follows a normal distribution according to the original paper. And for the relationship, which is accelerated carbonation with permeability, we will not use it directly. We will define a conditional PDF for a given KT rather than using directly the relationship with associated uncertainty in parameter A. And this is not easy solution, it is not trivial, and we'll address next. In order to develop it, this function is the key element of the present approach. In order to develop it, we used the data that we get available in the work of Nevesh. This is the data in a log scale as the original work of Tiruzzi, and we work with cement type 2. And we have 47 pairs of KCA and KT. We obtain the coefficient of correlation, and we test the F statistic, which is the null hypothesis, in order to ensure if we have a correlation or not, the relationship between KCA and KT. And we find that we have a relationship between KT and KCA, as you see here. And this is conduct us to reject the null hypothesis and the existence of the relationship. After that, we should to ensure what follows. If we consider that KT is a constant, deterministic, KCA, what follows? Can follow a log normal distribution according to the literature and follows a Weber distribution. We tried both distribution, and we found that the log normal distribution is the most suitable distribution for our research, for the relationship. This is formula 6, is the function, the log normal function, the D is the standard deviation, and the mu is the expected value. Now, introducing the expected value and the relationship from the accelerated carbonation and air permeability into equation 6, we will obtain the equation 7 as you see here. You see here that we have two parameters, the D and the A. And in order to estimate them, we use the maximum likelihood estimation method. After several steps, mathematical steps, we get here, writing in blue, the log maximum likelihood function. In order to get, we will maximize this equation as you see here, we will maximize it. We use this spread check. We use the tool, the solver, and after that we get our parameters, which is the A and the D, as you see here, with the B fixed, 0.415. After that, we will replace these parameters into equations, into equation 7, and we obtain our log, our conditional probability density function. And I told you first that we tried Weibull and log normal. And we told that log normal is the most suitable, and we plot PP plot and QQ plot. And what we found that there is a fair adhesion of the PP point and QQ point to the equality line, confirming the adequacy of using the log normal distribution for the conditional PDF of KCA for a given KT. This is some plots, and you see here that follows a log normal distribution. After that, now arriving to the probabilistic service life design. In order to solve this integral, we need much mathematical effort, and sometimes it is impossible. In this case, we use the Monte Carlo simulation. And with Monte Carlo simulation, we will generate random variables, and with this random, and we will generate as much as we know. We generate 60,000 value for the lifetime function, for the cover depth, for the KE, and for the KCA. And the input information for the Monte Carlo simulation is given here. For the cover depth, we used the truncated normal in order to not get negative value, which is have no sense. And for the KT, it is deterministic. We use 16 values with a log scale. And for the KA, we have the XC3 and the XC4. And I prepared some videos in order to see how we apply the Monte Carlo simulation. After that, I will get 60,000 service life. And from this, I will give you one example here, which is the PDF in histograph, which is the probability density function, and the CDF, which is the cumulative distribution function of service life. For KT, this 0.1, and for the cover depth 30 with exposure plus XC4. As the service life increases, the probability of distribution decreases, and the cumulative probability of failure increases. After that, what we developed these figures, which is the probability of failure as function of KT for the 5 cover depth, for the 3 service life, 50, 100, and 300, which is the record, for both XC3 class and XC4. This is an example for 50 years, this is for 100, and this is for 300. After that, we can't work with the probability of failure 100%. For the XC3 and XC4, we should to limit the probability of failure. In this case, we developed the design chart in the XC4 with 6.7 as a probability of failure. And you see here the KT as function of the cover depth for the 3 service lives. And also, for the XC3, we work with the probability of failure 50%. You told me why XC4 6.7 and XC3 50%? Because we have dangers in XC4 more than XC3. And as expected, the required air permeability coefficient increases with the increase of cover depth. And also, it is also worth noticing that higher air permeability coefficients are allowed in exposure class XC3 compared to XC4. After that, we compared our results with the previous specifications. What we found that we have a fair agreement with the previous durability-based design. Here you see with Astra, and here with Williado Viat, here as you see. After that, we developed these design charts for the XC4 and the XC3. And here the KT, and this is the service life, and this is for each cover depth. And the feature of this method, it is the ability to make a probabilistic service life design. And the feature of this method that is relied on a test method that we can apply it on site. And an example I will show you here the feature of this method with an example. And this is not applied for simple construction. It is for high importance construction as bridge or nuclear stations. And an example, I will give you here an example. For example, if we consider that I have an owner and want a service life of 50 years. And when we went to see the area, we find it that it is in XC3 exposure class. And according to our approach, I will give him, in order to ensure the durability against carbonation, you should to make 50 and 0.3 kT Torrent test method. After that, the feature of this method that I can assess or verify this design specification on site. I will go to see how much the cover depth and how much the Torrent test method value, which is the air permeability. With the non-destructive method, with Torrent test method, I can test any area as much I want. I will not recourse as Sambiro or other test method. And when we verify, we find that we have a non-conformity. We find that we have 45 and the KT increases 0.7. And this is, let us to have an update on the service life. The new service life is 20 years rather than 50 years, and the loss is considered as 30 years of loss. This is very bad, but the things that is important in our approach, that now we can make a strategy. I will not wait 50 years. Before, in 20 years, I will see if the corrosion started or not, in order to make a strategy of reparation. Now, arriving to the conclusions of this part, I write here many conclusions. I will start with the fifth one. Departing from existing knowledge and experimental data, a new service life design methodology concerning carbonation-induced corrosion is proposed. To the knowledge of the authors, this is the first full probabilistic approach based on the results of a test method applicable on site. The specification resulting from the current approach are in general agreement with the previous performance-based specification for reinforced concrete durability. The feature of the proposed approach is the ability to make a probabilistic estimation of service life via cover depth and KT. The real service life can be estimated through as-built assessment of the design specification and loss of the service life due to deviation from the design specification. Non-conformity can be made. In such approaches, we should to have the limitations. The limitation of my approach is just for cement type 2. I can't apply it for cement type 1 or cement type 4. And also the conversion from accelerated to natural is for current CO2 concentration. If additional sources of CO2 are expected, example car parking, then the service life design shall not be undertaken following the proposed methodology. In this approach, the specified KT value is a characteristic value whose conformity shall be assessed following procedures and for criteria following the proposed reference, as you see here. As a future research, I write here many researchers. The important is to develop a performance-based service life design based on durability indicator in the case of Algeria environment using Taleh and Kharshi test method. And also to develop the same specifications for the cement type 4, we develop it, and for cement type 1. And also the estimation of service life in the case of RDL project. Because we know that design with tunnel design, they are threatened from carbonation or the chloride more than the other structure. And we should to estimate the residual service life of these structures. And also we need to enlarge the database in order to have reliable D parameter. After that, I special acknowledgement to the professor that I worked with him, and also to my father and mother that are here, and also to my wife, daughter, sister, and her husband, Mirza. Finally, we have one life too. Thank you so much.